Okay, let's do a carbonate polyatomic ion Lewis dot structure. It's got some different things than our earlier Lewis dot structures, and there's some important parts to it, so go through all of it. Well, we've got a polyatomic ion here, which, even though it's an ion, is covalently bonded within itself, and we're going to figure out how those electrons and how the molecule looks. So, carbonate, what's our next step here? We'll go to, of course, the valence electrons. We've got carbon and oxygen, and here's carbon in column 4 and oxygen in column 6. So with one carbon, 4 valence electrons, because that's always the first step, how many electrons we have to play with. Next, of course, is the oxygen, which we have 3 of, so we've got 18 more electrons. We're up to 22 electrons now, but there's also one extra thing. This is a charge. If you've got a negative charge, then that means that you've got to deal with extra electrons. And those extra electrons are going to have to be incorporated. I mean, they're tossed into the mix here to make our molecule, so we're going to put in 2 more electrons. And let's see how we do that here. We'll get that tossed in here. Let's move forward. 2 extra electrons. There we are. We have a total now of 24 electrons. 2 negative 2s and 24 electrons to deal with. And so let's keep going. Next step is to set up our skeleton here. Again, central atom. Usually that's the first one, but not always. But you'll see. With some experience, this will come automatically. A carbon with 3 oxygens around it. Now, because it's a polyatomic ion, the best thing to do to notify everybody, to warn them that, hey, the electron count's off, is to use these brackets with a negative 2 up here to indicate that. You won't be marked wrong on an AP exam, but really, this is the proper way of doing it. It's easy enough. Sometimes you forget, but if you remember, toss that in. So we're going to have to take our central atom and make some bonds with it. So let's do that. Let's draw those little lines in, and of course there's 1, 2, 3 lines. But of course they're not lines. They're shared pairs of electrons. So 2, 4, 6. We've taken care of 6 of these electrons. We have to get rid of all of them, all 18 eventually in this structure, that are left behind. So once we've got our central atom bonded, the next thing we've got to deal with are the surrounding atoms. They will need that low potential energy set of 8 electrons. They already have 2, so all we've got to do is our count, 6, 6, and 6, and that's easy enough to deal with. Our first 6 and then the others. So we're taking 6, 12, 18, and we've used up all of our electrons. There are no more electrons in the cupboard to toss into this molecule. And this is where we're having a problem, because there is another rule. The low potential energy of an octet for the central atom is going to be necessary and important. Unless you've got boron or aluminum, a structure really should have a central atom with at least 8 electrons. So what are we to do? We don't have any extra electrons we can add, so we're going to have to pirate some electrons. Just borrow them, if you like, from the other atoms. So where are we going to get those? Here's a choice. We can slide over this pair of electrons and put them into a bond. The oxygen will still have those electrons. They'll still be sharing them. They're no longer an unshared pair, but they'll be shared. And the carbon will get the extra pair of electrons that it needs for that octet. Now, we could do that on this side too, or on this side too, whichever you like, whatever you prefer. I picked here. Now, don't forget, you've got to slide those electrons off. Sometimes people will put an X there, but the original electrons can't be left there. You've got to put them into the bond, and there they are, and I'm going to draw them in as a line. So there we go. There's that extra line, that extra bond, that second set of shared electrons. Now there's a problem with this because there's only room for 2 electrons a shared pair, one orbital, directly between these two atoms. Getting another pair in there, even though it's easy to draw in for us, doesn't work. There's no room. There's going to be repulsion, and the first bond is the sigma, and that's a straight one in between the two atoms. Nice, simple, and straightforward. This second one is really, really strange. Now, the Lewis dot diagram, we refer to these, we've got our first bond as the sigma, and the second's given a different name, a pi bond, because it is very different, and it uses p orbitals, which you'll see some diagrams of. And really what it is that some p orbitals are involved, and they're parallel to one another. So you actually get a bond that is above and below. So it's not interfering with our first sigma. Both electrons are in this arc, both top and bottom. So the pi bond is one that is really, this is a closer depiction of it, but it's hard to draw. Imagine drawing these all over the place. So traditionally, it's drawn as a second straight line, a simplification, but an AP student and a chemist knows that this is very special. It's got actually a cloud of electrons above and below this thing, and that makes the pi bond pretty reactive. If you want to get some electrons from a compound, this is the first place I look in a chemical reaction. Look for some pi bonds to pick up an electron or two from, which is going to be our study of change thing. So, okay, that's our pi bond. You can draw it in our Lewis dot diagrams as a simple line. Now, analyzing this molecule right now that we've drawn, we've got all of our electrons are taken care of. Let me get my little drawing tool here. This oxygen has its octet. This oxygen has 8 electrons too. And now I'm going over here, and whoops, no, I didn't want another one. Here, I'll draw this in here. This one, and we'll get rid of that. Delete. This oxygen, 2, 4, 6, 8. It has 2 unshared, not unpaired, they're pairs, unshared electrons, and it has 2 shared. So that's fine. And here, we'll look at our carbon in the center. It has 2, 4, 6, and then our pi bond, a shared pair, 8. So this is excellent. We've got everything that we need to create a molecule that you'd expect using the Lewis dot diagram. Now, this central atom has 3 sigmas and 1 pi. Now, there's something extra you have to know about this. And let me get back there. There's our pi bond. I'm explaining it again. That when we do our count for domains, our steric number, oops, this is wrong. In fact, I can pick up an X here. I should have, I'll just get a stamp. Let me pick up a stamp, and where's my X? I've got X here. Here is an X. That's wrong. This isn't 2. This is going to be 3. Our steric number is 3 because we have 1, 2, 3 sigma bonds. We only count unshared pairs of electrons and sigma bonds for our steric number. There really are only 3 things that are around our central atom. That's our steric number of 3, and that's going to be important for our shape of our molecules later on. Okay, now that we know the steric number is 3, we can go on to the next complication. So this is the first complication is, pi bonds are never included in our domain count. And I'll put this 3 here. And maybe I can do a little bit of erasing here. Okay, erase. There. No one will know I made my error. And I'll put my steric number of 3. Not 4, but 3. Pi bonds are never included in our domain count. Okay, now, next complication. Double bonds are stronger than single bonds. There's more attractions between the two atoms. There's our sigma bond, and then there's our pi bond, and both of those are going to pull the two atoms closer together. And typically, a carbon-oxygen double bond is 122 picometers. A single bond is only 143. Again, you've got only one pair of electrons pulling these two guys together that both these atoms are attracted to by the nuclei. So in this atom, you'd expect a shorter bond, and two long bonds. But when we experimentally measure this, we find out that's not so. And it's pretty logical why it can't be so, because really, that double bond could have been put here, where we decided to, or to the left, or underneath. These three are identical locations. They're all ideal situations. So there were three possibilities for this electron to be at. And electrons are sort of wavy, and they have these quantum effects where they say, okay, all these places are the same, so why not just reside in all of them? When you have a resonance structure where there are identical locations, the equivalent locations, I should say, then the bond doesn't just stay at one spot. It, in effect, averages out everywhere. Now, when you're asked to draw resonance structures, you show all the possible situations, as we have here. Another way of depicting it is to show the bonds sort of averaged out. It's called pi bond delocalization. And it's a very interesting factor. When pi bonds delocalize, they've got a very unusual energy. In fact, these delocalized bonds are responsible for some of the most brilliant colors you'll see in chemistry, and we'll deal with that later on. But the actual bond length is 122 picometers. Remember, the single bond length, if it's just a single bond, was a big 143. A double bond was supposed to be 122, but the actual experimental is 128, and they're all identical. There is not one location that is favored over all the rest. So there are a number of new things in this carbonate. First of all, we had a charge. Second, we had to make a double bond. And third, we found that a double bond is very unusual. It's a pi bond, and it's not involved in the steric number. And then finally, a double bond can maybe be put in different locations where it will average itself. So quite a bit in the carbonate, very important molecule here. Okay, this is a longer video, but it covers almost everything you need to know in terms of Lewis dot diagrams, except for one complication, and that'll come up in the next one. Okay, that's it. We're closing down. We've wrapped it up.